So tonight we're going to talk about amines and amides. Amines. So nitrogen has 5 valence electrons, and so it will form 3 bonds because you've got 2 that are paired up here, and you've got 3 single electrons available. So nitrogen, carbon forms 4 bonds. Nitrogen is going to make 3. So an amine is when you have a nitrogen group that's attached to either an alkyl group, a cycloalkyl group, or a aromatic ring or an aryl group. And basically an amine has an amino group on it. This is NH2 because you've got the third bond is into the R chain here. The same case here and here as well. So you can have primary amines where the nitrogen is attached to a carbon chain and it has 2 hydrogens. An example here is we've got a nitrogen connected to a methyl group with 2 hydrogens. You can have secondary amines where you've got 2 R chains connected to the nitrogen and then only 1 hydrogen attached here. An example here, this could be a ring. So you've got a methyl group, that's 1 R. You've got a benzene ring, that's the second R. And then here is the 1 hydrogen. So this is a secondary amine. And then you can have tertiary amines where you don't have any hydrogens anymore. It's all 3 R groups. So an example here is actually a bad example. Ignore that. I don't know where that came from. Holy schmoly. I'll have to get you a better example of that. You can also have heterocyclic amines where the nitrogen is in the ring itself. If you have the nitrogen in the ring, but it has a hydrogen hanging off the side, then this will still be a secondary amine. If you've got an R chain hanging off of that nitrogen, then it'll be a tertiary amine. So it's in, and then this is an R, and this is an R, and that's an R. So that makes it a tertiary. And here you got an R chain, and this is the hydrogen, so that makes it a secondary. And here's just some examples, not expecting you to memorize these or anything like that, but these are some fairly common amines. You can see here that you've got the NH group in here. Here's one that has 2 nitrogen groups in it. This pyridine is a particularly nasty chemical. Really smells bad. I think we were talking a few weeks ago and I was telling people that my wife used to complain when I worked in the commercial laboratory, and one of those was this nasty smell in pyridine. So how do you name amines? We're going to look at primary amines first. So you select the longest chain that includes the nitrogen, just like we've done with our other things. You're going to name the parent chain using the corresponding alkane name, but then you're going to replace the E at the end with amine. Then you're going to number the chain nearest to the nitrogen, indicate the location of the nitrogen in the chain, locate and name any other functional groups. So here we've got 1, 2, 3, 4 carbons. So that would be butane. So that becomes butanamine. You drop the E and add amine on the end. And then 2 indicates that this amino group is on the second carbon in that chain. Here we've got 1, 2, 3, 4. So again, it's butanamine. and it is one butanamine because this amino group is on the very first carbon here. But then we've got a methyl group hanging off of here on the third carbon, so that's 3-methyl-1-butanamine. You can also have diamines. So here we've got an amino group on this end, an amino group on that end. In this case, the E is retained for ease of pronunciation, and then you add diamine to the end. So here we've got 1, 2, 3, 4 carbons. So this is butane diamine, and then it's on the first one and the fourth one. So this is 1,4-butane diamine. Do all amino acids contain a nitrogen if N makes an amino group? Yep, you're exactly right. We'll see that when we get into the biochemistry side of things. Your amino acids are going to have nitrogens in them. For secondary and tertiary amines, you use N's to denote the functional groups that are attached to the nitrogen. So here's a case where, let's do this one first. So here we've got 1, 2, 3, 4. So that's butanamine again. It's on the second carbon, so that's 2-butanamine. And then we have a methyl group out here, making this a secondary amine. So this gets named capital N methyl 2-butanamine. And this tells you that this methyl group is attached to this nitrogen here. In the case of a tertiary, so we've got 3 R chains attached, you just use the N's as well. So here the longest chain we got is a propyl group. So this becomes propanamine. This is on the very first carbon of that chain, so it's 1-propanamine. And then we've got N-dimethyl because it's 2 methyl groups here. So you get N, N dimethyl 1-propanamine. Any questions there at all? I guess these are just some more examples I put on here. So here we've got 1, 2, 3, 4, 5. So this is a pentanamine. It's on the third carbon as your ammonia group. So it's 3-pentanamine. And then we've got a methyl group on the nitrogen, and we've got a methyl group on this carbon here. And in this particular case, we can number starting from either side. So we can go 1, 2. So that's your first dimethyl. And then N is for this methyl group. So you get 2, N dimethyl, and then your 3-pentanamine. And then here is an example where we have our longest chain is 3 carbons, so that's propanamine. It's 1 because this nitrogen is attached to that first carbon. And then we've got an ethyl or a methyl group and an ethyl group. So this becomes N-ethyl, N-methyl 1-propanamine. On slide 5, when it says R, is the R anything that is attached? Go back there. So R is just a carbon chain. So this could be any length of a chain or a ring or whatever. I don't know if that answers your question or not.
Yes, thank you.
Okay. And notice I put a prime here because this isn't necessarily the same as this one. And this has a double prime because it's, these could all be different. Okay, that's the one I just did. All right, functional group priority. Amines fall right below alcohols. So I reproduced this list from a previous chapter, and I just added the amine in here. It's above the alkene and below the alcohols. So if you have different functional groups, then you have to decide on your priority again. So
Where would ethers and esters fall on that list?
I don't have them on this list. I'll have to take a look at that. Ethers and esters priority. I'll take a look at that, let you guys know. So if you have additional functional groups on there, then you have to look at that priority. Here we have a carboxylic acid, so that's going to have higher priority. So you look at the number of carbons here. We got 1, 2, 3, 4, 5. So this is pentanoic acid. And then this is going to be on the, actually this should be 2 amino pentanoic, no 3, that's right. 1, 2, 3. So this is 3 amino pentanoic acid. So this gets treated as a functional group if it's lower in priority than other functional groups on the chain. Does that make sense? Here we've got a alcohol, but an alcohol is still higher priority. So this is going to become an amino group. We've got 3 carbons, so that's propanol. This alcohol is on the first carbon, so that's 1 propanol. And then now we've got you have to denote that it's a methyl amino group, because you've got this methyl group out here attached to this guy. So that's N-methyl amino. And then the 3 denotes that it's attached to this third carbon. Any questions there at all? If you have aromatic amines, just like we had phenol was a benzene ring with an OH, a benzene ring with an amino group is called aniline. And so if you have substituents on it, you use that base aniline. So we've got aniline here, and then again you start numbering with the amino group. So this is 2,3 dichloroaniline. And here we've got an ethyl group attached to our amino group, but this is still an aniline because we've got the benzene ring here. So you denote the ethyl with an N. So this is N-ethyl aniline. Any questions there at all? Ziggy Planton.
Here you go.
No, stop. Let's try to get to turn my light back on. Ziggy Planton. Thank you. Turn my light off. Okay. You can have isomerism with amines. So here is a case of we've got this 1, 2, 3, 4, 5 carbon chain with the amino group on the end. But here we've got 4 with one of the carbons off of here. So this is a skeletal isomer, and it's changed because the carbon is in a different place. Here we have the example of a positional isomer. because the amino group goes from the second carbon in to the first carbon. But these have the exact same molecular formulas. These have the exact same molecular formulas. So these are isomers of each other. Trying to remember why I have this slide here. Did we already talk about naming? We talked about naming these, right? Oh, these are isomers of each other. So here we have N dimethylaniline. So it's an aniline because you got the nitrogen on the benzene. But now we have a hydrogen over here and you've got the methyl group moved over here. So 3N dimethylaniline is an isomer with this guy as well. So these two are isomers of each other. So this would be an example of a structural isomer or skeletal. Okay, so try to name this guy. Give you all a minute. You can type the name in the chat. All right, looks like we're building a consensus. Yeah, so N-ethyl 1-pentamine. So we've got 1, 2, 3, 4, 5 carbons here with an amine group attached to it. It's attached to the very first carbon. So this is 1-pentamine, pentanamine, and then that's N-ethyl. How about trying to draw 4-bromoaniline? And just say when you're done and we'll take a look at it. All right, Kayla's got it. Anybody else? Riley's in. Give you another bit here. All right. So did you get something like this? Like my funky H here? So this is our aniline part. And then you've got 1, 2, 3, 4. So that's 4 bromoaniline. Good. All right, physical properties. Methyl and ethylamines are gases at room temperature, and they smell like ammonia. But other amines are usually liquids at room temperature, and they often smell like rotting fish. So fish, when it rots, is actually producing amines. Yeah, gross. I agree. Boiling point. This isn't blood pressure, it's boiling point. Amines can have hydrogen bonding between themselves. So you see here we got an amine, we've got an RNH2 and another RNH2. This hydrogen has got a partial positive because of this very electronegative double electrons here. And this is going to have a partial negative because of the double electrons. And so you can get bonding between these. So this will increase the boiling point, makes these more stick together more, takes more energy to break them apart and turn them into gases. Amine, though this nitrogen-hydrogen bond, however, is weaker than the hydrogen bonding in an alcohol. And therefore, this means that the lowest boiling points are going to be alkanes because they don't have any polar substituents at all. And the next highest is going to be amines, and the highest will be alcohols in terms of boiling point. Solubility, amines are water soluble due to hydrogen bonding between them and water. So you got a water molecule over here, and again, this is going to have a partial positive. This has a partial negative, and so this will make amines water soluble. These are polar. Any questions there? Amines are weak bases. They will accept a proton from water to produce an ammonium ion. So here we've got very simple methylamine, react it with water. It can act as a weak base and accept a proton from your water molecule and be in solution with a hydroxy ion. You can also form amine salts. So amines react with acids to form amine salts. So we have here an amine reacting with hydrogen chloride or hydrochloric acid, and you will get a H2 plus, so it picks up the hydrogen here onto this NH, so it's now got a positive charge, and then you've got this negative chloride ion left over here, and this is an amine salt. They are named by listing the ammonium part first and then the negative ion. So this would be called dimethyl ammonium chloride. You've got the two methyls there. So this is dimethyl ammonium and then chloride for your negative ion. Pharmaceuticals will still use older naming conventions that you often see on labels. Again, I'm not going to test you on that, but I just want you to be aware of it. A common name that you often see for this is dimethylamine hydrochloride. You convert amines into amine salts when you put lemon on fish. So lemon has citric acid, and that will react with the amines and make them amine salts. And that helps cut down on that fishy odor. All right, reactions with amines. So you prepare amines. You can react ammonia with a halogenated alkane. That's the RXs. So this is some long chain or ring with the halogen on it. In the presence of a strong base, will pop off that halogen and put the R onto your nitrogen, and you lose one of your hydrogens here. So you get RNH2. So this is a primary amine. You can take that primary amine and react it with a halogenated alkane, with, again, in the presence of a strong base, and make a secondary amine. And you can take that and react it again and get a tertiary amine. So again, you might get a question like this on the test. I don't know, I don't remember, but we could say if you slightly oxidized this, what would you get? Or if you strongly oxidized it, what would you get? And you could go all the way out to a tertiary amine. Any questions there? And you can't really have a quaternary amine because this nitrogen only forms 3 bonds, but you can create a what's called a quaternary ammonium salt by reacting a tertiary amine with a halogenated alkane, the presence of a base, and you will get a salt here where you have attached the 4th R group, R chain, onto that nitrogen. So it's now got a positive charge, and then it forms a salt with your leftover negative charged halide. Okay, alkylation of amines. Chemical reaction. An alkylation reaction is a chemical reaction where an alkyl group is transferred from one molecule to another. Alkyl halides react with ammonia and amines in a basic environment to produce other amines. This is kind of just a rehash of what we just went over. So you've got ammonia reacting with this to give you a primary. Then you can react it again to get a secondary, a tertiary, and if you go even further, you get a quaternary. So I guess that's just a duplication of what I already had. And here's some examples. So here's ammonia with an ethyl bromide in the presence of sodium hydroxide. And you're going to get this ethyl amine, ethanamine, with a sodium bromide as a product and water as a product. A secondary amine. So we have the production of a secondary amine. So you've got a primary amine here, this ethyl amine, reacted with a methyl bromide in the presence of sodium hydroxide. And then this is going to give you your 2 R groups on either side, the ethyl group and the methyl group. And then you can take a secondary amine and again react it with another halogenated alkane, and you get your tertiary amine. So you've got an ethyl group and a methyl group still there, and then it adds this R chain, this methyl group, onto there as well. And then your salt, I took this tertiary amine, reacted it again with methyl bromide, and you get this your ammonium ion and then your halide ion. So just some examples of those formulas. So if I took this and reacted it with this in the presence of NaOH, what would be the name and the structure of the resulting compound? Go ahead and give that a whirl. You can just put the name of the compound in the chat.
Get your pills done? Yeah, it's okay. I know, I got cheese ravioli, and then they put more cheese on top of it. Too much cheese.
Yeah, don't worry about the
Provolone,
side
yeah,
products.
sandwich.
But you're right, salt and water.
Provolone sandwich. That's what we did. Oh, you don't have to now, but that's what we do because we don't want to get cold and difficult.
Anybody else?
You still can catch it. Because they say put it there. And anybody else now, doesn't have it. A lot of people out there didn't get vaccinated, so we're taking a chance. Well, all you do is ask them. You stay wait long enough to go.
Close my door, I guess. All right, anybody else? So did you get something like this? So we've got this methyl group coming off of the nitrogen right there. And we've got this propyl group coming off on this side.
Where's the
And
purple coming from?
right here, 1, 2, 3.
Oh, sorry.
And then this is your ethyl group, and this is your methyl group. So that gives you N-ethyl, N-methyl, 1-propanamine. So you've got your 3 carbons here, so that's propanamine. The nitrogen's attached to the end. So that's 1, and then you've got the N-methyl, N-ethyl.
So when it comes to placing the N, like into the naming, so do you just, I don't know how to say it, sorry. So you have the N in the middle, and then on one side you have an ethyl, and on the other side you have a propyl. Is that where you're getting those?
I'm not sure I'm following you.
Can you explain, like, in the naming how you have N?
Oh, so you've got 1, 2, 3 carbons here. That's these 3. So the N is attached there. So this is propanamine. And this nitrogen is on that very first carbon. So that's a 1. And then now you designate anything that hangs off of the nitrogen with an N. So this is N-methyl, because that's a methyl group. and this is in ethyl because that's an ethyl group. You just alphabetize them so you get in ethyl, in methyl.
Got it. Thank you so much.
All right, so
Why wouldn't it be two propanamine? Right? Why wouldn't the N replace the chlorine?
I'm going to replace the chlorine. Oh, and put it in here.
Yeah.
That actually could possibly be the case. I'll have to go back and look at that. I don't know if these rearrange. You wouldn't think so. Oh, no, that isn't it either. Yeah. I'll go back and look at that. I'll let you guys know. All right, some real world cases of amines. So, two major stimulants, caffeine and nicotine, have amino groups in them. Yeah, I'm not going to test you on this, but just so you guys are aware of this. Many amines have pleasant odors. Methyl 2-pyridyl ketone actually gives you the odor of popcorn, but you see this heterocyclic amine right here. And 2-methoxy-5-methylpyrazine, a heck of a name. You've got two amino groups in here. This gives you the odor of peanuts. A very important one is hemoglobin. We'll look at this again when we get more into biochemistry, but you have these heterocyclic amines set at the very top of this large molecule, and you have an iron ion that sets in the middle of all of these, and an oxygen comes in and is attached to this iron, and that's how the oxygen is carried through your blood, through your blood to oxygenate your body. And so this is a very important amine structure that is used within the body. And by the way, the reason why cyanide is so deadly is cyanide fits in here just as better than oxygen. And so it will replace the oxygen and put itself in there. And then that causes you basically to suffocate because your body isn't getting oxygen anymore. That is a very acute toxin. It doesn't take a lot of cyanide and it happens fast. You're dead. You get the blue lips and you're a goner because you're essentially starving your whole body of oxygen. So it just has a greater affinity for this site than the oxygen site does. Amines also exist in neurotransmitters. These are chemicals in your body that transmit the electrical signal. And so we have norepinephrine. This is produced in the adrenal glands in your body. And this is used to tone your blood vessels. This chemical here, you can see this amino group here on the end. Dopamine is produced in the brain. Low levels of dopamine affects Parkinson's disease, and taking cocaine boosts dopamine, and that's why it's so addictive. Is you get a pleasure sensation with high levels of dopamine. And again, you've got this amino group here that's attached to a benzene ring with two hydroxy groups on it. This gives you dopamine. Serotonin is also produced in the brain. It is used to regulate body temperature and sleep. And serotonin is often used in treatment of mental illness. So some forms of mental illness are due to the body not producing enough serotonin in the brain. And then a big one is epinephrine. Again, we've got our amino group here. I think we just had epinephrine here. That's dopamine. Oh, epinephrine has an extra hydroxy group right here. That's the difference between dopamine and epinephrine. This is also called adrenaline. We're all pretty familiar with that. When you are in pain, fear, or excitement, your body can dump massive amounts of this, produce massive amounts of this, and it gives you tons of energy all of a sudden in a big burst. And it elevates your blood glucose level, so you're getting that sugar boost. It also elevates your heart rate, which gets more oxygen into your system, and it also boosts muscle strength. And this is often called the fight or flight drug. So when you are in very excited or very fearful and extreme pain, your body is producing a lot of this. We have a family story, and you guys have probably heard of examples of this as well, but in our family, there's a story of what do you call it? Just the bed of a dump truck fell on a little girl, and my grandfather picked it up and lifted it off of her. That's something he would not normally be able to do. That was a boost of muscle strength and his excitement or fear, combination of both, trying to save that girl. I actually don't know how the girl did. All I heard about is him lifting that off of her. This elevated heart rate and higher sugar in your body, though, also can cause you to lose your finer motor functions. So have you guys seen, like, horror movies or thriller movies where the person's panicking and they're trying to, like, put their keys in the ignition or something and they can't do it? They're shaking and they can't. That's because they've lost their fine motor skills. When you're in that fight or flight mode, your body is much more focused on getting you out of the situation, and so it's giving you all that energy to fight or run, and because of that you tend to lose your dexterity. Histamine's got an amino group in it as well. Allergens cause this to be released inside of the body, and this causes hay fever and the like. And when you take an antihistamine, it's inhibiting the production of histamines in your body in reaction to these allergens. Alkaloids have nitrogen containing compounds in them as well. These are usually come from plants. They're very strong painkillers, and they're also very addictive. So morphine, codeine, and heroin are all alkaloids, and all of them have amine groups in them. Amphetamines, you guys have probably heard of amphetamines before. Methamphetamine, also called methadone, is an antidepressant. Methylphenidate goes by the common name Ritalin, and this is a chemical that's used to treat ADHD. And if any of you have asthma like I do, you sometimes need to use a bronchial dilator for your lungs to open them up, and with an inhaler. And the common chemical used there is methoxyamphetamine. And again, in all these groups, you see these amino groups in here. And Novocaine is used by dentists as a numbing agent. And again, you've got this amino group and an amino group here in this long chain. All right, any questions about amines before we move to amides? Okay, an amide is where a carboxylic acid, where the OH has been replaced with an amino group. And so here we have a primary amide. You've got RC double bond O, and then an NH2 here instead of an OH. And this would be a primary amide. A secondary amide would be where you have RC double bond O in, and then another R chain over here. And then, as you could probably guess, a tertiary amide is where you've got essentially three R chains attached to this nitrogen, but this carbon has a double bond O. So this is a tertiary amide. You can have cyclic amides. These are called lactams. So you've got a double bond O here, but then you have this amino group in the chain of the ring, and this is called a lactam. Any questions there? So when you're naming amides, you use the carboxylic acid name, but you replace the oic acid with amide. And then you append the names of the groups attached to the nitrogen to the front of the name using the N prefix as a locator. So we'll see some examples here. So here is methanamide. So you've got one carbon here. This would have been originally with the OH here, but now it's got this amino group. So this is a methanamide. Here we've got two carbons, so this is ethanamide. Propanamide, 3 carbons. Here is 4 carbons, but there's a methyl group hanging off this end. So again, when you're naming this, you're just going to go with butanamide for the 4 carbons. And then this methyl is on this 3rd carbon here, so it's 3-methyl butanamide. And then here we have an example where there's a chlorine here and a methyl group here. So this has got 3 carbons in the main chain, so that's propanamide. And then you've got 2 chloral and 2 methyl propanamide. Any questions there? In the case of secondary and tertiary amides, then you're back with using your N designation. So here we've got a methyl group hanging off of this nitrogen. So we've got 3 carbons in our chain. So that's propanamide. And then this is going to be N-methyl propanamide. And then here in the case of a tertiary, we've got 2 methyl groups off of this nitrogen. We've only got 2 carbons here, so that's going to be an ethanamide. And then it's going to become N, N dimethyl ethanamide. If you have aromatic amides, it takes the root name benzamide. So just like we had benzaldehyde and benzoic acid, here we get benzamide. So it's a benzene ring attached to this amide functional group. This is just your R chain, but it takes the root name benzamide. And so here we have benzamide with a methyl group off of that second position. You start numbering with your amide group where it's attached to the ring. So this is 2-methyl benzamide. And then if you have R group out here, then that gets the N designation. So it's still benzamide, and then it's N-methyl, because you've got a methyl group out there on that nitrogen. Any questions there at all?
So the only time we use N is when there's something coming off of the what's it called?
The nitrogen.
NH. Yeah.
Yeah, when you have R chains off of that nitrogens, when you use that N designation.
Awesome. Thank you.
So try to name this guy. Give you a few minutes. Okay, looks like we've got answers coming in. And yes, so we have 1, 2, 3 carbons, so that's propanamide. And we have a methyl group on this nitrogen, so that's N-methyl. And then we've got a bromine on that second one, so 2-bromo-N-methylpropanamide. Good.
Okay, so we have to go with the alphabetical then for the bromo versus N
Yeah,
stuff.
yeah,
Okay.
you're going to alphabetize the bromo and the methyl. All right, try to draw this guy. Do you remember what a phenyl group looks like? Just tell me when you're done. Now, what's a phenyl group? Anybody remember?
It's like a benzene ring.
Yeah, it's a benzene ring. So that might help people out. Anybody else? Okay, Kayla's done, Riley's done. Done but confused. I like that. Yeah, this is maybe a little tougher one. Okay, so you've got your benzamide is this whole thing. This is going to be a tertiary amide because you've got two R groups. In this case, they're phenyl groups or benzene rings. So this is N, N diphenyl benzamide. That was kind of a tricky one. Any questions there? Did that unconfuse you, Julia, or make you more confused?
We'll both be honest, but it's okay.
Okay, most amides are solid at room temperature. Amides have high boiling and melting points because of amide hydrogen bonding. So again, here you can have your slightly positive hydrogens attracted to these slightly positive oxygens on other amides. But a primary amide is going to have higher boiling and melting points than secondary, and secondary will be higher than tertiary because you've got fewer hydrogens to bond with. So if this is an R here instead of a hydrogen, then you're not going to have any bonding going on over here, right? And so that means that a secondary would have less opportunities for hydrogen bonding than a primary. And then a tertiary, of course, doesn't have any hydrogens to bond with. Water solubility, 1 to 6 carbon chain amides are water soluble because they can form hydrogen bonds with water through either the oxygen, the hydrogen, or the nitrogen. So this is a complicated looking little critter here. We've got the oxygen here with the partial negative charge can be bonded with this partial hydrogen in the water molecule. This hydrogen here that's partially positive can bond with this nitrogen, which is partially negative because of these electrons. And then you can have this nitrogen on this one being attracted over to the oxygen on this water molecule, so forth and so on. When you get larger chains, then it gets harder for these bonds to happen. The water molecules can't get in there to make these kinds of bonds, and so they won't be as water soluble. So that's why it's with smaller size chains. Unlike amines, amides do not act as bases. Remember, amines acted as a weak base. Nitrogen won't accept a proton because it's partially positive. And the reason why is this is due to something called resonance. So remember, we always said at the beginning of this class that we draw these things as if they're really, always look like that. But the reality is that it's always somewhere in between. So you can have this amide. So we've got an R carbon double bond O attached to our amino group. This oxygen has these 2 electron pairs out here, and the nitrogen has 1 electron pair. The reality is that this sometimes looks like this, where you have the electron go in and form a double bond here. But now you've got this nitrogen with 1, 2, 3, 4, because you got 2 hydrogens out there. So this is going to have a positive charge on it. And this bond has gone out into the oxygen. And so this is going to have a negative charge. So this is called resonance in that it exists in both states back and forth very quickly in nanoseconds, if not picoseconds or even low, even greater. But in other words, these don't just stay this way. They can resonate back and forth in these structures. And because of that, this nitrogen will not accept a proton like it does in amines. So it will not act as a base. Does that make sense? Any questions there with that? Remember, we said that with a benzene ring, we draw 3 double bonds, but actually it's all the carbons within the benzene ring. We go back here to, that's really why we draw these as a circle, because you could have the double bond here, here, and here, but you could also have the double bond here, here, and here on the alternating carbons. And the reality is it's kind of a mix of all the above. That's another example of this type of resonance. Okay, reactions. I think we're actually making pretty good time. I was worried. Do you guys want another break or do you want to keep going? What say you all? Keep going? Okay. So preparing amides, this is called amidification. You can take a carboxylic acid, so we have RCOOH, and it can react with ammonia, NH3, and you form water here with the OH from the carboxylic acid and one of the hydrogens from the ammonia, so you get water over here. And then this nitrogen will attach into this carbon that's on the double bond, and this gives you a primary amide. So you've got RC double bond O in H2. So this is a primary amide. You can react a carboxylic acid with a primary amine. By the way, all of these take heat and catalyst. And again, you're going to form water. And now you're going to have a secondary amide because this amine has this R chain over here. So now you're going to get RC double bond O in HR. And remember, these R's don't have to be the same. And so this is a secondary amide. And then you could take carboxylic acid and react it with, yes, you guessed it, a secondary amine. And this will form a tertiary amide. So we've got this nitrogen has got essentially 3 R groups on it. And so this is a tertiary amide. Any questions there? So essentially then, an amide has this acid part from the carboxylic acid, and it has an amine part from the amine that it reacted with. And this is going to give up the OH, and this is going to give up the hydrogen in order to form that. So if we put the OH back on here, we get our parent carboxylic acid. In this example, it's propanoic acid. And if we put the H back, if we split this and put the H back onto the nitrogen, then you're going to get the parent amine that produced this. And in this case, it's methylamine, because you've got this methyl group here on it. So there's an acid part and there's an amine part to an amide. If you react a amide with water and heat in neutral solution, you'll basically reverse that reaction. So here we have an amide reacted with water. You're going to get back the carboxylic acid and the amine. So we're putting the OH back on this carbon over here, and you're putting the hydrogen here back on this nitrogen over here. So you're reversing that reaction. If you do it in the presence of acid or bases, however, you get salts, and it depends on which one. So in the presence of a strong acid and water, you'll get a carboxylic acid, but you'll get an amine salt. So this nitrogen here, so it splits it again, but because of this strong acid being present, it's going to accept a proton and get a positive charge and then form this salt complex with your halogen anion right here. But if you do it in a basic environment, so here we have an amide with a strong base, sodium hydroxide, apply heat, you'll get the flip side of this, you'll get a carboxylic acid salt and your amine. So this, it's still going to cleave, but your amine will pick up that hydrogen, but your carboxylic acid is not going to take on the hydrogen here. Instead, it's going to be just an oxygen with a negative charge. There's no H here. And then that will form a salt with your cation. So acid produces an amine salt. Base is going to produce a carboxylic acid salt. Any questions there at all? And you can polymerize amides. So a diamine, so remember a diamine is where you've got an NH on either side of a chemical compound. It will react with a dicarboxylic acid to produce polyamides. So here we have a dicarboxylic acid. This is a COOH and a COOH. And then here we have a diamine. We've got an NH2 on this side and an NH2 on this side. And you'll take the hydrogen off of the nitrogen, the OH, the hydroxy group, off of one side of the carboxylic acid and give you water. And then these two will connect together and you will form this long chain with a carboxylic acid group on one end and an amine group on the other end. But this can keep going on, reacting over and over again. And so you get this repeating unit here of an amino group and a carboxylic acid group over and over again, causing a polyamide. Any questions there? Some examples of this is nylon. Nylon is one of the first polymers to be generated. Nylon 6 is got 6 carbons in here repeating over and over again with an amino group on one end and your carboxylic acid group on the other, and it just repeats n times. Nylon 6,6 is a 2-set one that just repeats over and over again. You're not going to have to memorize this. I might ask you, is nylon, what's an example of a polyamide or something, but not expect you to remember the structure or anything like that. Kevlar is what is used for what? What's Kevlar used for? Anybody know?
Bulletproof vest.
Bulletproof vest. Yeah, this is made up of aromatic rings, and the hydrogen bonding gives it more rigidness. So here we have this amino group on this end and a carboxylic acid group on this end, repeating over and over again with these phenyl groups in the middle. And what happens is that you get bonding between the double bond carbon double bond oxygen on one chain with the nitrogen and hydrogen on the other chain, and this gives you cross linkages, and that makes these very strong and compact polymers, which, you know, just thousands and thousands of layers of these on top of each other happening on both sides here, and that gives it that resilience to the kinetic energy from a bullet coming in. But yet it's flexible enough that it's not like you're wearing steel plate or something. You know, it's a lighter weight material. But Kevlar is an example of a polyamide. Polyurethanes. Polyurethanes contain an ester and an amine unit. So we have an ester amine unit here that's repeating over and over again in this polymer. These form very elastic fibers. Polyurethanes are used in furniture, life preservers, packaging, and so forth. Polyurethane is also used on burns as a skin substitute because they'll only pass oxygen and water through their barrier. And so it aids in the healing. It protects that burned skin and keeps it from bacteria and all that, but yet also keeps it hydrated. And so polyurethanes are used for synthetic skin as well. Some real world uses. So your kidneys eliminate excess nitrogen from your body. We'll see this again when we get into the biochem side, by forming urea, which comes out of your body in urine. And urea is an amide. Certain foods and dehydration can cause gout, which is a buildup of uric acid in the joints of the body. Anybody have parents with gout at all? It runs in my family. Luckily, I have beaten the gout syndrome by figuring out that a lot of mine was coming from dehydration. So I drink lots of water so that I don't get bouts of gout. I used to get them a couple times a year, but I haven't had one in a long time. It's extremely painful. This uric acid crystallizes, and it's like little spikes in the joints of like your foot or your ankle. Some people even get them in other joints. So by keeping myself well hydrated all the time, I don't tend to get this, but both my parents suffered from gout really bad, and I inherited the tendency for that. Certain foods also can cause this buildup of uric acid in your body. Gout is also called the King's disease because red wine and very rich foods can contribute to gout. And so that's why it's called the King's disease. Uric acid can also cause kidney stones. Yeah, I didn't remember that. Good to know. Kind of makes sense. Your kidneys are trying to get rid of this, and it can't. Melatonin is produced in the pineal gland and this regulates sleep cycle. And again, you see this amide group here in this molecule of melatonin. Barbiturates are used as a relaxant to aid in sleep. If you take it too much, it'll kill you. You can see here that it is an amide. It's got an amine group, but also a carboxy group here as well. The reason it's called barbiturates is the inventor named it after his girlfriend, Barbara. Thought that was kind of a funny little historical note. Lidocaine is another numbing agent used by dentists, and this is an amide as well. You've got that carboxy group right here, but then you've also got an amino group here and a tertiary amine over here. Acetaminophen is the most widely used over-the-counter painkiller. It's popular because it doesn't irritate intestines like aspirin can. And acetaminophen, again, you've got this amine and a carboxy group, so it's a amide. It's got an amide functional group in its structure. And I can't believe it. We made it by 8:33, according to my clock. There's some problems here. Again, I gave you some 4th edition and 7th edition problems to try out. Are there any questions about amines or amides at all? I think what we'll do next week is we'll not only review chapter 6, but we'll kind of maybe do a review, if you guys would like, over 5 and 6 in preparation for the test. And maybe I can come up with some more problems for you guys to try out. Does that sound like a good idea? Everybody likes that? All right, so we'll spend a little bit more time on that next week then. Okay, well, you can hang out and do problems, or you can split, whichever you like to do.
Have a good night. Thank you.
Yep. Good night.
Thank you. Thank you. Bye. Thank you.
Thank you.